Consider a source of sound. I'm going to draw it like this asterisk and indicating sounds just emanating from that point. And some of the sound waves are traveling here to the right. They're going this direction. And let's say I've let enough time lapse that I can count 3 of these waves. Here's another one. Here's a 4th one coming out. And these have traveled away. So this one was created at least 3 periods before. This one 2 periods before, 1 period before, and just a little bit, some fraction of a period. This one was released. So the time of this is a little bit between 3 and 4 periods ago. Now these waves have a wavelength. We could measure them. We can look at the molecules of air, and we can measure how far apart these compressed regions are to see their wavelength. And we know that they're traveling at a speed v in air. Now the curious thing is what happens if instead of this source just sitting here emanating these or creating these waves and they're traveling away, what if the source is also moving in that direction while it's creating these wave fronts? What happens? Okay, so let's draw that scenario. Here is the wave, or here's the source to start, and it creates, and at the same, the same earlier time, it created this wave, which then traveled this far. Okay, so it would have traveled from here to here. In that time, I'm going to call that distance x1, and it's going to be equal to v times t1. Okay, it just traveled this distance because of its speed and the time it took to get there. Now, suppose that this is moving at a speed vs, okay, and in 1 period it travels this far. So vs equals, xs, the distance the source traveled is equal to vs times 1 period. And when it got to here, it released the next wave, which then traveled for a time t1 minus t. And so the next wave would have gone, let's say, to about here, and this distance, I'm going to write it out here, I'm going to call it x2, is equal to the speed of sound, because it's still traveling through the air at the speed of sound, but it had less time to travel. It traveled a t1 minus the period. It was released 1 period later, and so it traveled that far. So my question is, what is now the wavelength? Obviously, up here, when the source was stationary, these waves were all the spacing between the waves was governed solely by the speed and then the frequency of the source. But now the frequency is the same, meaning the period's the same, the time spacing between them the same, but this one was released closer to that one than it was over here, so it had to travel a little bit further. And the question is, how big is that wavelength now? What is this new perceived wavelength? I'm going to put that prime there to indicate this is a perceived wavelength, with unprime meaning that's the inherent wavelength in the medium for the unmoving source. Well, we can see that all these distances should add up. This is the total distance from the original position of the source to the first wavefront, okay? And then these 3 distances add up to equal that one. So we can write that x1 is equal to xs plus x2 plus lambda prime. And then solving for lambda prime, we get lambda prime equals x1, which is v times t1, minus x2, which is v times t1 minus the period, minus xs, which is vs times the period. Okay, solving for that, we can see that this vt1 minus vt1, those cancel, and then I have a minus v times a minus t, gives me a positive vt, the period, big T, and then minus this last term, vst. So my perceived wavelength is equal to my period times the velocity of air, the velocity of sound in air, sorry, it's velocity of sound in air, minus the velocity of the source. Okay? Now, that is a fine relationship just right down there, except when we're measuring sound, when I hear a sound, a tune or a tone coming off, coming out of a speaker, I can tell its frequency much better than I can tell its wavelength. And so I'm going to rewrite this and say lambda prime is equal to V minus Vs over over this period. Now this period was the inherent period of the source, so it's the true frequency. So that's going to be my true frequency, no prime there. Okay, and I'm going to just note this shape, because in another video we're going to combine this with another case. But for this particular case, let's go ahead and take this further. This lambda prime is the perceived wavelength. Let's express this in terms of a perceived frequency. So lambda prime would be equal to the velocity perceived. Okay, so that would be V prime over the frequency prime, the perceived frequency. That's going to be equal to this V minus Vs over the frequency. Okay, so this is the perceived frequency we hear. What is the perceived velocity of these waves? Well, if I'm over here listening to it, these waves are still traveling and hitting my ear at this speed. So the perceived speed is the true speed of sound. And so with that, knowing that that's just V, I'm going to do a little bit of rearranging, bring the F prime up and the F up, and then bring this down to solve for F prime. I'll leave some of that algebra for you. That ends up being F prime, the perceived frequency, is equal to the original frequency, the true frequency of the source, okay, times the velocity, remember this is the velocity of sound, over the velocity of sound minus the velocity of the source. Okay, so this is a way of being able to measure the perceived frequency when we know the true frequency, the velocity of sound, and the velocity of the observer. Now what I want to point out here before we leave is there's a minus sign there that came from our algebra. And so if the source is moving towards the observer, we call that approaching. If the source is approaching the observer, the value here is positive, but there is an algebraic minus sign in front. So we're minusing a positive value when the source is approaching the observer. Had I done it the other way, where the source was receding from the observer, okay, we would have gotten a plus sign here. So we can leave that as a minus sign and just note that if the source is receding from the observer, we plug into this value a negative number, and so we have an algebraic minus sign and a negative value, which gives us an overall positive. And so this minus sign is consistent if we use that convention. So for approaching, Vs is positive. For receding, Vs is negative. This minus sign stays there all the time.